power sector utilities are gearing up. We are proud to conduct the series.
Shweta, you became, you are not audible now. You are not audible now.
Accidental mute.
So am I audible?
Oh,
Yeah, audible.
You are not audible now.
Oh, sorry for that, sir.
Yeah, go on, continue.
Okay, now it is my duty and definitely my honor to invite Professor V.K. Damodaran, sir, mentor and advisor of IEEE Kerala Chapter and IEEE Live Senior Member for the introductory speech. Sir, the mic is all yours.
Okay, thank you. And thank you, the KCB team and the Power and Energy Society team. It has been a wonderful opportunity. And I would only say that this is actually marking a new beginning in the power scenario and in a way overall energy scenario of Kerala. That this kind of a discussion purely originating from the practicing engineers of Kerala State Electricity Board Limited is heir to the professionals who are really enthusiastic about the issue of solving what we call the problems of energy transition. In fact, the energy transition in India basically started somewhere around 2010 to 2013 period. The previous energy transition, which was experienced by the whole world, has been in 1913, started not by any professional or engineer, but none other than Winston Churchill, not as Prime Minister of the United Kingdom, but then the head of Navy of the Royal Navy of England. They were actually ex officio members of the parliament. And it was there that Churchill, with his eloquence in the parliament, made a very stirring appeal to change over from coal to oil for the Royal Navy fleet. So the parliament was actually taken almost by storm, and they all unanimously passed the resolution. Then the resolution went to the secretariat. There, one lower officer immediately had a question, but where is oil for England? There was no oil. So naturally, it went up to the higher ups, and Churchill was actually called. See, you have actually made a recommendation, but we have no oil resources. We don't have even any oil source. How do we carry out this? Suddenly, in his brain, an idea came. He said it is very simple. Anywhere, anytime, oil is mined, that will be bought by royalty. It will be England's material, and we will market it all over the world, for which a company was floated. The rest is history. That is British Petroleum. So the transition to oil, after that, a major transition, though electricity was introduced in a big way in almost all countries, in our country as well, but the real energy transition into renewable energy started. Maybe initially it was Germany who pioneered it. And that was almost from the beginning of this 21st century. And in India, we seriously thought about almost a century after Churchill's transition call in 1913, that is now in around 2013. And still we were not very clear. And many of our utility organizations, most of them at that time were not companies, but currently most of them are companies, and they are now seriously thinking about how the transition has to be affected. And there are one or two or three issues. I'll very briefly sum up that. One thing is about the finitude of resources. That is why we wanted fossil fuel to be off from the energy scene to the extent possible. But it is something impossible to be eliminated even during this 21st century. So we will have to live with oil and coal at least till we tide over half of this century. Maybe it may be another 10 or 20 years more.
Sir,
we don't know.
I think
it all depends. Now, coming to this, there are again three problems.
Yeah.
One thing is demand is on the increase. So we can say it is a surging demand, and impact of climate change has been felt more, and the burden of its responsibility or the source has been put on the shoulders of energy production and use. That means the major way. And the third thing is you have actually the looming scarcity of resources, as I have mentioned. And so we started using renewables, and wind and solar are now in the major bracket. In the whole list, these two have actually surfaced up, with wind first and solar next, which will be solar first very soon. But they have actually the problem of intermittency, and this can only be overcome by balancing. This can be by storage, this can be by other sources. So what we expect is, at least by the middle of the century, starting from 2030 onwards, the major energy sources will be three: WWS, wind, water, and solar, in which currently we have actually more than 1,300 and odd GW of water in large hydro, small hydro, and some of the newer technologies. And that is going to increase a little bit in the conventional way. Solar is going to surge ahead. China has already started surging starting from 2011, and nobody is able to stop them. So in the current scenario, we will definitely have increase in this, and ultimately our electrical or energy infrastructure will be dominated by renewable energy sources. But that is, we are only talking about resources or the sources, but much depend upon how you utilize them and how you integrate these energy resources into a conventional, traditional, and somewhat not much updated technologies. I mean, I don't mean that basic technology has not been updated, but as far as integration is concerned, they are not being made receptive to that kind of new additions. So this is where we have actually enormous amount of technology problems. But we also find that the bridging of gap between environment and industry, because requirements are conflicting, is again a major problem. And how to fit these newer resources into a normally and unprovocative demand supplier is again philosophically a question which technically we have to solve. And it has to be solved by the current engineers in the field and also by the young engineers who are actually what we call the budding engineers who are still in the college and the young professionals who are just about to practice. And this is going to be a continuing challenge. And with the COVID also in place, we find that energy integration has certain newer problems that we didn't actually anticipate till 2019. This is where the question is. And that is where I find it is highly appreciative that the engineers who are in the utility come up with questions of search on the kind of problems and search for the literature elsewhere and experience elsewhere, because we find that even very small, tiny countries where no technological leadership or even technological stature has been, could be claimed, has actually entered into energy transition in a raw way, but successfully. Like Cuba in 2005 under Fidel Castro. It was actually a policy decision driving an energy transition in that country, which none of us studied in detail, because what is there to learn from Cuba for us? Currently, a small country in East Africa, Rwanda, almost a destroyed, annihilated country, which is actually just coming like a phoenix bird. They have, even during COVID times, introduced robotic doctors who receive patients who are suspected to be COVID affected. You can't even imagine, even in our country, we don't have system. So the question is actually how we get our professionals prepared to take these challenges and be adventurous and trying to find solutions which are actually what we call temporally and spatially suitable for us, for the time and for the problems. And this is a challenge of researchers in the academic area, as well as every average professional in the utilities. And it is my belief and my hope and my prayer that this spirit of inquiry and spirit of discussion with academic persons and experienced persons who are either in the field or out of the field to come up with solutions which are relevant to the society is something which is worth praising. I think the spirit, let it remain, and my good wishes, and thank you all.
Thank you, sir, for being a standing example for all the budding engineers out here. And thank you so much for your valuable words. Now, I cordially invite Engineer Ajit Gopi, sir, Vice Chair IEEE PS Kerala Chapter, for taking up the mic for the introduction of our speaker. Sir, please.
Thank you. Thank you for the invite. So thank you, sir, VKD sir, for the inspiring words. Actually, it was an initiative by IEEE PS Kerala Chapter based on suggestions of VKD sir, Chandramohan sir, and all the veterans. So we just thought that we could do this kind of a session, a webinar series, which can bring a lot of ideas around, because the precious people will be, of course, the utility people who can come and join this webinar series and share their ideas. So just before introducing Biju SS, Engineer Biju SS, I just want to give an idea of what exactly we are going ahead with this program. So we we have 6 talks scheduled, part of this webinar series from experts from the Public Utility KCB Limited. The first talk is, of course, by Engineer Biju SS, Executive Engineer Transcript, which is scheduled today, immediately starting. The second is tomorrow, actually. The talk from Engineer Pradeep B. He is currently the Deputy Chief Engineer and in full charge of the Chief Engineers under Commercial and Planning Department of KCB. He will be delivering a talk on the changing role of utilities, of course, a very relevant subject. And the next talk is scheduled on 25th on dam top and floating solar projects by Engineer Laiju MS as the Executive Engineer, Renewable Energy and Energy Conservation Division of KCB Limited. And next is 26th, we have Engineer Joseph VK, Chief Engineer of REEF, who he is speaking on the total utility scale power plants and the EV initiatives of KCB. And on 29th, we have Engineer Madhu of the Saura rooftop program. He will be detailed the rooftop solar, the existing scenario, and their strategies and all. And last will be Engineer Harikumar KP. He is actually the treasurer of IEEE IEEE Kerala Chapter. Harikumar sir will be delivering a talk on power system SCADA. So these are the 6 talks scheduled, part of the great webinar series planned with experts from KCB Limited. So I'll be introducing Biju sir, Biju SS Executive Engineer with the Transgrid Kottayam KCB Limited. So Biju SS is, we got an very experienced, very renowned person in the power system, from the power system side. I'll just give a detail of his profile. He did his BTech in electrical engineering from College of Engineering, Trivandrum in 1991, and his MTech in power system from College of Engineering, Trivandrum. He has got extensive experience in the field of power system studies, power system operations, EST, switchgear design and testing, engineering and execution of substation projects, engineering of hydroelectric projects, installation and testing, commissioning and operation and maintenance of ST and EST substation equipments, control and relay panels, SCADA and communication systems, etc. He has successfully designed and developed a protection relays-based control and monitoring system for substation automation. He has got extensive experience in power system analysis using ETAP and important softwares. He has experience in power system analysis and analysis tools like SIME, PSAF, Power World Simulator, MyPower software, etc. He is experienced in ground design using AutoGrid Pro software, and he's presently working as Executive Engineer Transgrid, as I said earlier, at Kottayam, and is in charge of construction of 400 kV and 220 kV JI substation and 400 kV and 220 kV, 110 kV multi-circuit, multi-voltage lines. So extensive experience of a powerful engineer from the power system side from KCB Limited. And he has worked with Alint, he has worked with the Al Haida Switchgear Company, Kuwait, and he has got extensive experience from ABB Germany and ABB Kuwait. And he has been trained in ABB Germany and ABB Kuwait and in various power system softwares from international field also. So it's a great honor for us actually to get to Sri SS Biju, Engineer SS Biju, on board for this powerful talk. Welcome, Biju sir, for on behalf of IEEE PS chapter I'm welcoming you for for the beginning of the session. Thank you for accepting our invitation.
Thank you.
The floor is for you. You know, sir. The floor, I'm leaving the floor for you. Thank you.
Okay, thank you. I'll start sharing my screen, okay.
Yes, please.
Okay, I hope all of you can see my screen, okay? It's clear?
Yes, Biju. It's visible. Go ahead.
Yeah, okay. So, good evening to all of you. I hope you are all having a nice weekend. As Mr. Ajit told, today's weekend webinar topic is on RE integration and the Kerala power system.
Biju sir, Biju sir, I have a small request to all the all the participants here. So if you have any kind of queries coming up, your doubts and all, kindly drop your queries in the chat box, and our team will collect it and consolidate it then for the later Q&A session. So kindly scribble your questions into in the chat box, so that can be answered later. Yeah, thank you.
Yeah. Okay, so like I was telling, today's topic is regarding RE integration and Kerala power system in general. First, in order to understand the challenges in the integration of RE in Kerala power system, we need to have a good awareness of KSB network. So today I am planning to give you an overall picture about the Kerala power system in general, its peculiarities, constraints, and the challenges faced. Okay. And the technology innovations adopted by KSCB to overcome these prior to discussing the RE integration. I hope this session will provide a backdrop for the upcoming sessions, because when you have listened to the upcoming sessions, you should have a thorough background of the picture of KSCB power system also. And today's session, I hope to give you that, okay? And I hope this session will provide you with a window into the KSCB system and RE integration in general, so that you will be able to make further explorations in this regard. We were talking about the challenges, we were talking about the technologies adopted and the framework that is there in adjusting to the RE integration. Okay. So first of all, before going further, let us look at the essential changes in the framework, the challenges that is being faced by the power sector nowadays. In general, all utilities are facing these challenges. There's a large liberalization of the electricity market. Now, we have two power exchanges coming into play, and a lot of large volume of trade is being occurring there. And there is consequent to that, there is a larger demand and an increase in the electricity transportation network. The demand is higher than usual, except for the COVID scenario now. It was progressively coming up. Compared to the previous years, the demand was very high during 2019, and it was expected to be very high, but due to COVID scenario, it has come down. But again, it has picked up. Nowadays, it is very high. So, consequent to that, the demand on the transmission network is also very high nowadays. Congestions are happening, and we have to address those things also. And second and fourth, the most important thing is the renewable energy sources. Now they are rising like anything. We are having ultra mega power projects coming up with 4,000 megawatt power projects coming up in southern region, and there is a high demand for the reliability of supply. That's a number one priority for the for government also, to provide reliable supply to the consumers, 24/7, 365 days supply to the consumers. And for that, the utilities have to plan for the maintenance and modernization, because almost all the equipments, all system in the utility are aged. So now it is a big burden of the utilities to plan for the maintenance and modernization or replacement of those equipments to meet the challenges.
Biju sir, a small request.
Yeah.
Is it in the presentation mode, sir? Is it in the presentation mode? Looks like it is just.
Is it?
I don't think this is the presentation. Can you just check it?
Hello, sir.
Yeah.
Biju sir, multiple screen use ചെയ്യുന്നുണ്ടോ?
Sir, can you put it into the presentation mode?
Yeah, I'll do that. See, I'll just come to this, then I'll put the from here.
You can just put it in the presentation mode.
Now it is clear?
Perfect. Go ahead.
Fine. So I'll go to present review also so that I can have that. Okay. So this is the challenges that's being faced with power sector. So before going further into this, how we are going to tackle this, we'll start with the overview of the Kerala power system. We'll have history also. That it was constituted in 1957. Just for those persons who are new to KSGB. Basically, it is constituted in 1957, and at that time, the installed capacity was only around 109.5 megawatts, whereas at the time, the all India capacity was around 30 to 23 megawatts. The transmission and distribution system voltages was from 3.3 kV to 110 kV with a consumer strength of 1.06 lakhs. At the time, the all India strength was around 32.076 lakhs. Okay. So what is now? At present, the installed capacity has come up only up to 2880 megawatts, from 109 to 2880 megawatts, whereas the all India capacity has gone from 30 to 23 megawatts to 373 gigawatts as of now. The TND system has grown from, in Kerala system has grown from 11 kV to 400 kV, whereas the national system has grown up to 765 kV and 800 kV DC. And we are going for 1200 kV UHV AC also. And the consumer strength in Kerala is around 128 lakhs. So this is the general picture. And when you look at the source-wise generation, you can see that Kerala is predominantly hydro. The blue one is hydro. Okay, so this is predominantly hydro, whereas in Karnataka and Tamil Nadu, it is predominantly, nowadays it's predominantly renewables. Earlier days, it used to be thermal, but nowadays it is predominantly renewable. And Andhra Pradesh, still it is predominantly thermal. So in a way, when you consider renewables, from a renewable point of view, this hydro is a boon for KSCB because we can balance the renewables with our hydro, which is having fast ramping up and ramping down capabilities. Whereas for the other states, it's a little bit difficult because if you see their hydro reserves are comparatively low, so it becomes very difficult for them to adjust to the variables of the renewables. But it is a bane for us also because we are highly dependent upon monsoon for our generation. Okay. And when you consider statistics, again, the recorded maximum was 4316 megawatt, around 4,300 megawatts, with a morning peak demand of 400 megawatt and a day peak demand of 3900 megawatts. And the peak consumption was 88.34. The typical characteristics is like this, that the morning peak, day peak, and peak consumption occurred on 23/5/19. The importance of that day is it was an election counting day, so that your morning peak, day peak, and everything went up. Okay, and when you see the per capita consumption, Kerala is having very low one, 595 units only, whereas the national average is 1208 units. And regarding the generation portfolio, we have solar at 5% and wind at 2% for the renewables, gas and diesel at 6% and thermal 13%, and predominantly by hydro at 74%. And in the consumer sector, if you look at it, this domestic is around 52%. We have high domestic part on for the consumption. It's around 52%, with the commercial coming second. Commercial industry is coming just behind. Irrigation and agriculture is the lowest one for Kerala, and others is around 11%. But the consumption, even though the domestic has the largest share for the consumers, the consumption is mainly by the commercial and power and energy industries. Domestic consumption is very comparatively low when you compare the commercial consumption. When you look at the larger scenario, when you compare with the other states in southern region, you can see the domestic part for the other states is comparatively low. They have the industries and commercial coming into picture, So that is a boon for them, but for us, it is a bane because we don't have any commercial, the industries coming up in Kerala. So the consumption, what happens is this creates a problem for us. Basically, our day, if you see the daily load pattern, the peak occurs in the evening and during the morning period also, because that's predominantly domestic. If the industries was there, we could have flattened the load curve. Our load curve is not flattened now because of the lack of industries. That's a problem we are facing, and that creates a problem for the renewable integration also. And this is the demand pattern which has occurred from June 6 to January 18. I didn't collect the data for 1920. I didn't put it there basically, but it shows a similar pattern. Kerala, if you look at the Kerala pattern, it is almost similar throughout the year. For the last 10 years, the ups and downs are almost the same. There is no change in that. So load forecasting as of now is very easy for Kerala, because if you see the load pattern, the demand variation is almost constant. That you can see in the next slide also. When you have the morning and peak demand, they're also following the same pattern. The evening peak and the morning peak, if you see, the ups and downs are almost the same. That's basically the reflection of the domestic usage, consumers usage. Okay. If it has been otherwise, it would have been totally different thing. So when you look at the consumption, we have the largest consumption from Jan to April and May, and the lowest during the monsoon period, beginning from July, August, and September. Again, it comes down on December because of the winter season. And the daily demand pattern, this is very important as far as when we talk about the renewable integration, because our base load is met by the CGS, central generation allocations. That's a constant one. We have around 1600 megawatt of central power allocated to us, out of which 1200 is continuously available. And next to that, this is the CGS sector, which is the base load. And next we have the LTA, long-term access, long-term contracts, which is there. These are 1100 megawatts. So these two are almost constant, round the clock. RTC, it is round the clock power, which plays a big role when you talk about the amount of renewables that can be integrated into the grid. And we balance the load requirement, demand requirement, by utilizing the hydro, which is this one, and the unscheduled interchanges which happens between this thing. And of course, sometimes we use system intervention also, load shedding also, but for this particular curve, system intervention was not there. When your demand exceeds your supply, when you have constraints for bringing power from outside, we go in for load shedding or system intervention, like bringing down the tap. One important thing about, good thing about domestic consumers is that like this, you can control the demand by controlling the voltage, because of the domestic users. If it is an industrial load, that would have not been possible. In India, only in Kerala state that is possible, because we can control around 200 megawatts, 200 to 300 megawatts, but just adjusting the tap to a lower voltage. So that is a big advantage for us. And this is one important thing about daily load curve. It's very predictable. And this is, if you see the smart metering regime, there is lot of opposition for smart metering, saying that from the load curve, from your demand curve, can easily, the privacy gets lost. In a way, it is true. If you see this, I'll just explain how it is being done. See, if you see this curve, from 30 onwards, that's a wake-up curve. People try to wake up. So at this point of time, the demand gradually increases from 5:30 to 6:30. You have induction cookers coming into picture, and all the fans, lights, everything coming into the picture, so that the load goes up. And again, after a certain time, the morning period, that high demand period is over, and when children goes to school, everything comes down. So that is the lowering of the demand. It's very clear from 7:30 to 8:30 during that period. Again, what happens is there's another hike when the office opens, 9:30 to 10:30. The office opens, official establishments opens. There's a hike in the load. And again, if you see government offices, commercial sectors, business hours, there's those come into picture, commercial business and all. Then there's a big hike. Okay, AC loads are there. Then again, morning tea, it comes down. There's interruption or shift changes is there in the factories. So there's a dip in the load. Then again, the lunchtime, again there's a dip. And this particular one is shift changes. Then school, colleges closing. That's also dip there. And again, the office closing time around 5:35 to 5:30. There's a dip. And again, there's another hike during this time when the TVs, everything gets on, evening time, lights, fans, everything comes up. Then the commercial establishment gets closed around 20:30 to 21 hours. And again, there's another hike when again the TV, news channels, everything comes up. And after that, siesta. Okay, the demand comes down. But what now we find is that the demand still goes up around 11:30 because of the AC load. During summer days, the peak demand happens around 10:30 to 11 when all the AC loads comes into picture. So that is something which is happening over the last 2 years, a typical thing. Okay, so when the smart metering, when you have the current signatures also, the load signatures also, it's very easy to identify the equipment that is being used. Okay, this is just based on the load that is being recorded in the substations. See, that's how we can identify the various dips and swells in the load curve. When you compare the demand projection, there's a 19th electric power survey was there, but the Kerala load is a little bit lagging when you compare with the EPS survey. So we have done a load forecasting based on our internal load pattern through a node-based load analysis. And what we have found is that our load will be growing to around 6,000 megawatt by 26-27. Even though the EPS survey has identified load growth to 6,000 by 24-25. Ours is, we think that will be occurring only by 26, 27, 28 during that period. But the biggest problem is our hydro. We don't have any hydro generation at all. There's no growth in that. It is stagnant because of the environmental issues and the clearance problems. We are unable to put up any new hydro projects. Even though we have around 6,000 megawatt hydro potential is available, we have only around 2,000 megawatt of generation. So after that, around 1650 megawatts is there as a constant basis. So rest we have to import. Basically, around 70% of the power is being imported from outside. So we are highly dependent upon the imported power. And if you see the current network, with the current network, the maximum import capability of a system is around 30 to 100 megawatt as of now. With the Cochin-Tirunelveli line, the newest line entry, we have around 30 to 100 megawatt import capability, and that gets exhausted by 2023. When we have around, when our requirement will go up to 30 to 100 megawatt, 30 to 147 megawatts. So we have to plan for new inter-regional connections, and that we are planned and it is being executed. We have one 2,000 megawatt HVDC terminal coming up in Madagaskar. That's going to be commissioned shortly by next month. And we have another 400 kV link coming up from Udupi to Kasaragod. That's under execution now, and is expected to come up by 2021 September. Okay, so hopefully we will be secure in that aspect. Again, current power system is like this. We have around 400 kV substations. 1 owned by KSEB and 5 owned by Power Grid Corporation of India. And we have 23 220 kV substations with another 1 owned by NTPC. We have 170 110 kV network and 65 60 kV substations with 158 33 kV substations. Altogether 470 substations are there. And we have around 11,575.
Amal,
where are you? 11,575 circuit kilometers of line also. Okay. Our main interconnection is with ISTS, and we have connection with ISTS, that Industrial Transmission System, as well as Karnataka and Tamil Nadu. Our 400 kV network connectivity is with ISTS. That is at Trivandrum. We have one substation Trivandrum, another one at Cochin, Madagaskar, Palakkad, and Arikod. The new one is coming up at Kasaragod. And we have one 220 kV connectivity also at Edamon with ISTS. With Karnataka, we have one 220 kV as well as 110 kV connectivity. At Kaniyampeta, we have 220 kV connectivity. At Manjeshwaram in Kasaragod, we have 110 kV connectivity. And with Tamil Nadu, we have two 220 kV connectivities. One is from Idukki, Udalpet, and the other one is from Theni, Shabarikiri. And we have one 110 kV connectivity also to Parshala from Ulithura. So this basically explains our interstate connectivity. This is the network that I already explained. we have 5 400 kV connectivity here as of now, and one is coming up here in Castrot, and another HVDC system is also coming up here to Thrissur. It's a 2000 megawatt HVDC, voltage source controlled HVDC, which is the second largest HVDC, VSC HVDC system in the world. One is coming, another one is coming up in England, but as of now, and at the time of execution, it's the second system in the world. Okay, it's a 320 kV, 2000 megawatt HVDC system. So the major constraints what we are facing, because we have to know the constraints also when you talk about renewable integration. The major hydro resources, all the major hydro resources are the southern part of Kerala. Northern part doesn't have any major hydro resources. It's only having a Kutyadi scheme, which is around 225 megawatt. When out of 2000 megawatt generation, hydro generation, and only 225 megawatt generation is there in the northern part. So it's really there is a scarcity there. And major plant additions are also in the southern part. ISS nodes, interstate transmission nodes, 400 kV nodes, they are also on the southern part. So when you look at it, northern region is deficit in supply of power. And that is one major concern for us, because you see every grid requires reactive support for voltage, for providing the required voltage. So the reactive power is being provided from the generating stations and a little bit from the ISTS also, because ISS nodes won't allow any reactive flow to occur through the interconnecting transformers. So basically all the reactive power has to come from the hydro stations. And this reactive power in northern Kerala has to be met from the generators in the central and southern region. So that is a huge loss for the KCB system. And the voltage in the northern area is very, very poor. If you see, it used to be around 182 kV, 180 kV in the 20 kV network. That is very poor voltage profile. So with the addition of Castrot 400 kV, we expect an improvement of around 8 to 10 kV there. And again, if you look at the growth also, this uneven growth, there are some of the districts like Trivandrum, Ernakulam, and Kozhikode is having very high growth, while other states, other areas like Wayanad, Kannur, Malappuram are having really, Palakkad are having really low growth, Idukki. So that is an uneven disposition of this load growth also. And again, generation addition, because of the environmental public issues, there is no nil generation addition, and the off-peak peak ratio is very poor. We have very low demand during the off-peak hours. That is one major problem we are facing, because as I have mentioned earlier, we have a constant CGS and LTAD supply. So that is to be there for meeting the demand. That's an RT, that's an around the clock power. So during off-peak period, it may happen that we have to start under those things, and there is a really low demand. So in order to overcome these problems, we have planned a pan-Kerala network, transmission network. That is called TransGrid, which is second generation transmission network planned by KSCB. It's around 10,000 crore project, which is mainly meant for improving the transmission network of Kerala. Because if you see the earlier slides, you will see that the 400 kV system, there's a break in the 400 kV network. You don't have connectivity between there was no connectivity between the central and the northern Kerala for the 400 kV system. Even 20 kV also, we don't have much circuits connecting the whole of Kerala. So TransGrid project is mainly meant for establishing the contingency criteria, for satisfying the contingency criteria, so that there will not be any failure of the system in the event of failure of one of the network elements. And we are planning to have a 400 kV pan-Kerala grid from north to south for transporting the demand, for transporting the power requirement of central and north Kerala. As I told you earlier, all our sources are in the southern part, so this power has been transported to the northern part with the minimal loss, so that we are planning for a 400 kV network. And along with that, we are upgrading the existing system also, downstream networks also, 33 kV networks, 66 kV networks, and 110 kV networks. But okay, it is planned in two phases. Phase 1 is from 2017 to 21, which is under execution. This is meant for evacuating the 2000 megawatt power from HVDC source, as well as for meeting the reliability criteria planned specified by the CEA planning guidelines, Central Electricity Authority planning guidelines. We have tendered this work into big packages so that we can attract serious and competent bidders. Now General GE, Siemens, Toshiba, these players are coming into picture for construction substations and lines at Atlantic, so that we have having good contractors for execution of these fund. It is being timely executed with only 18 months for substation construction, very time constrained work. And we have planned green corridor projects also for evacuation of RE, because we are facing severe constraints in the evacuation of renewable energy power, utility scale renewable energy power. We have proposals for wind evacuation in Agali, which we cannot evacuate due to the lack of transmission system there. And we have several proposals for the Attapadi, for the Ramakalmed area also. There also the transmission system is not developed. We cannot evacuate any power. In Kasaragod, we have lot of barren land capable of having solar power, the solar parks. There also we are facing constraints in evacuating the green power. So under the scheme, under this transit project, we are planning 3 major green corridor projects with MNRI funding. We are hoping to get the fund from green corridor project funding, green funding from MNRI. The phase 2 works basically is meant for improving the system reliability and security. All 33 lines we are planning for ring system in 33 kV, for upgrading the existing 6 kV to 110 kV and 20 kV like that. So it's basically for strengthening the existing network. After meeting the security criteria, we'll go in for improving the existing network so that we will have 24/7 supply without any interruption. Even in the outage of one of the feeders or transformers, we will not face any system constraints. See, the main problem what we are facing is right of way. That's the most important and severe thing in Kerala. Not only Kerala, everywhere it is the same thing now, but in Kerala it is very severe. So what we are doing is we are going to use the same right of way. Whatever we are having, we are going to use the same thing. That's why we went in for technology absorption. We have gone in search of technology that is currently available, and we have observed almost all the technologies that is made available now. So what we are planning is to use the same right of way 20 kV lines for upgrading to 400/20 kV. That is the first time in India that we are used one single circuit 20 kV right of way for upgrading to 400/20 kV. That's the first time in India that even the PGCL has done that. KSB has designed towers for using the same 22-meter right of way. Normally, we require 46 meters right of way for 400 kV, but here we use only 20-25 meter right of way for establishing this 400/20 kV network without any additional acquisition of land. We use UV strings and polymer cross-amps for that. That's first time, almost first time thing. Then we use the existing right of way 110 kV DC also for upgrading to 400/110 kV DC. That's being under construction now. We are that is also a first time in India, you can say. There is one used by PGCL for upgrading 110 kV DC to 400 kV single circuit, not a double circuit, but we are using for 400/110 kV DC circuit, multi-circuit for the same right of way. And again, we are using 110 kV lines for upgrading 20 kV using the same right of way, using narrow-based towers. 66 kV to 110 kV using the same, using monopoles. That's also a new one in Kerala. We are using monopoles for that. And again, we are going for using this reconducting of the existing ACSR conductors with the high temperature low sag conductors, HTLS conductors, which has got a higher current carrying capacity, around 2 to 2.5 times more than the ACSR conductor, with which we can use the same towers. You don't have to replace the towers for using the HTLS conductors because they have the same mechanical properties as the ACSR conductor, but they have very low sag also. Because normally when you load the conductor more, the sag will increase. That's basically a problem for loading. But for the HTLS conductors, you don't have any sag at all because the sag is very small. So that technology also we are using, but the cost is somewhat bit higher than the ACSR. The technology we are using, okay, there's a cost component in that, but we are forced to go in for this because of this constraints that we are facing in KSCB. This was not there for let's say some 5 years back because we didn't have this sort of technologies available at that time. So there was no development in the transmission sector. We only had an addition of 2 to 10 kilometers lines per year or something like that. But now, because of this technology integration, it's a boon. We could go in for massive expansion in the transmission network. So what we can expect? So once this transit project is over, we will have very good backbone with the several 400 kV lines in the grid. By 23-24, we can expect this Mysore, Wayanad, Kasaragod, Wayanad, Arikot, Udupi, Kasaragod, Udurpet, Palakkad, and Madakatra double circuit line, Madakatra Kochi's double circuit line, Madakatra Arikot double circuit line. This is constructed by KSB with the narrow-based towers. This Madakatra Arikot DC line. This is the first one I am talking about where we use the single circuit 220 kV right of way for having the 400 by 220 kV multi-circuit multi-voltage line. And Tirunelveli Kottayam Kochinis line, which is already over. Kottayam substation is coming up. Tirunelveli Edaman Kottayam Kochinis line, Edaman Trivandrum North, Tirunelveli Trivandrum North, Tirunelveli Edaman DC, and the 2000 megawatt HVDC link. So we are going to have a very good power transporting network in Kerala with this. And the substation, what we are planning is like this. During 2017-22, we are going to have around 9 for 220 kV substations, 9 plus 2 actually 11 220 kV substations and 2 400 kV substations. Out of this, Elangur in Manjeri is already commissioned. Kodamangalam, Chalakkudi, Kodamangalam, Kalur and Aluva. Kodamangalam, Kalur, Aluva and Kunnamkulam, they are going to commission by December. And Virinam is also expected by next year beginning. Chalakkudi and Virinam, they are going to be coming into picture by first quarter of 2021. So all these substations will be available by before March 2021. And A2N also will be available by March 21, Talasheri by the end of the next year. Kottayam 400 will be available by 21 end or 22 beginning, and Wayanad will be available by 22 beginning. And Thorovur, Vengalur, Ignalapada, Mannarkad, Shastangota, Panyal, and Pathanthita, they are expected during the period 2023. Nedaman also 400 by 2023. So this much expansion is there for that 10,000 crore project. Finally, the grid will be looking like this. We will have, say like this. Earlier we used to have a break here. We didn't have any interconnection at this point and at this point also. So there was no 400 substations towards the northern side. We had only at Arikot. Now we will having a 400 connectivity from Trivandrum to Edaman, Edaman to Kottayam, Kottayam to Cochinist, Cochinist to Madakatara, Madakatara and Palakkad, again to Arikot, and then Wayanad and Kasaragod, and then to Udupi. So this will be a pan-Kerala link, longitudinal link from south to north. And looking at a little bit in the power system operation, that I'll just give a brief of that also, because renewable integration basically has to have a knowledge about power system operation also. We have a national level NLDC with a backup LDC at Calcutta, NLDC at Delhi, and we have 5 regional load dispatch centers because we have 5 electrical regions, north, east, west, northeast, and south. And corresponding to it, we have 5 regional load dispatch centers, and then these are coming under NLDC. And under each RLDC, there you have a state LDC. So we have 33 state LDCs coming in, operating in the region. Okay, the hierarchical level is like this. And the main function is like this. They have to do the operational planning. They have to do the scheduling of energy, power, real-time monitoring and control, post-dispatch analysis, and market operations, including metering, accounting, and settlement for energy transactions. So these are the basically the grid that is being that is the screens available in the NLD. They can have a complete overall view of the 220 kV networks, complete view of 220 kV networks, and major 120 kV substations. They can have real-time flow status of the flows between the interstate transmission lines. What is being scheduled from various generating stations throughout the region. What is the entitlement for Kerala, and how much we are getting, how much is being scheduled, and what will be the price of electricity for each time block, and what will be the frequency. Those things will be available in a single screen. And they can have the this is actually the price per block for what is the frequency, and this frequency linked rate. So you can see the UI rate also. They can see, and based on this, they can do the market operations also. When the price is low, they will back down the hydro, and they will go in for market purchase and all stuff. This is a very short screen, so I'll just skip through this system overview. Then north and south overview. Okay, these are screens available in LDC. This is just for the viewers, knowledge only. And again, what is the traditional utility challenges? The traditional topologies like this, we have power station. It is a radial network. Basically, it is the radial flows are always radial. As of now, before the onset of renewable energy, the topology was always radial. From power station, we step up to transmission network, and power flows per transmission network to the distribution substations. They will step down there and go into the distribution network, and finally to the consumer through the LV supply. So basically, it is a radial flow. There was no issues with respect to that. There was no protection issues. Nothing was there. But now what happens is with the renewable thing, we have a centralized and distributed generations. Both are there. So we have microgrids coming into picture. There are intermittent generation, wind and solar. There's truly intermittent. We cannot predict that also. There's a multi-directional power flow, which creates problem with the protection systems. They have load encourages everything with the load adaptive protection. And the operations based more on real-time data, because we have to have real-time data to operate the grid. Well, now it is a real nightmare for the load dispatcher to operating the grid. It's really unpredictable. So pausings are there. So we need to have the operation based more on real-time data. Then the energy storage is also coming into picture with the electric vehicles and the energy storage. This is going to be the next generation topology. So there we will have multitude of challenges. So what are the other challenges? The profitability, that's a major one. We have to reduce the outages. We are forced to reduce the outages nowadays because as for any other sector, profitability is a big concern for the utility also. We have to reduce outage duration also. That means our maintenance, our outage planning and outage management should be more professional in outlook. And we have to reduce the maintenance cost. That's another important thing. And we have to reduce the losses also. As I told you earlier, the transmission loss is comparatively higher nowadays because of the transmission of this reactive power and all that stuff, because of the lack of generation in northern part. So we have to reduce the losses also by going in for higher voltages. And the environmental issues are there, like we don't have any generation addition as such. Even large scale renewables is also not possible because of lack of land, high dependency on import, calls for efficient interconnection for effective distribution of available resources. We have to manage with the available resources. So for that, we need to have a very good interconnection. That's why transcript has come into the picture. And the right of way, difficult to get new right of way. That's a big challenge. Litigations, encroachment. Everywhere we go, we face litigations, encroachments. Everything is there. Even under the lines we are facing, we are having buildings coming up. When we plan for new upgradations and new works, what we found was that most of the buildings are coming directly under the existing lines. So because of that, we are unable to move, construct new lines because of encroachments, because they will go into court, get stay and all that stuff. So it's very difficult for us to move ahead. And the forest clearance, that's a big headache. Even for the existing lines, we are unable to draw through the existing right of way because of these forest clearance issues. We are unable to pave the lines, new lines, because the forest clearance will not be issued. That's another big headache that what we are facing now. Even for renewable integration, sometimes even as of now, even the hydro, small SHGVs also are considered, even not the SHGV, even the HGVs are considered as renewables nowadays. So when you have new SHGVs coming up, you have to construct new evacuation lines. And most of the SHGVs are in the forest areas. So constructing a new line again is a problem because of this forest clearance issues. So what are the technology drivers? As I told you, the main technology drivers are for reducing latency losses. That is why we are adopting the new technology. We have to give reliable power and sustainable power also. That is, the sustainable power means basically renewable power. And we have to achieve more with the existing infrastructure and make the most of the available energy. And finally, we have to integrate the renewables. So these 6 points, these 6 aspects is the main drivers for absorbing the new technology into KSCB. So what we did, that's the next thing that I'm going to say. We are going for generation automation. That's for optimizing the generation. We are going for generation automation. We are planning floating solar systems in our reservoirs. We have canal top solar already executed. We have hybrid generation also. We have planned for remote communication and centralized monitoring. That's also there in the generation. This is all almost except for floating solar, all the other things have come into picture in generation. In the transmission network, we have network automation that's already there. SCADA is already there. Digital base are under execution. That's for the smart grid. We have digital base coming into picture. Not 100% digital, but 70, you can say semi-digital. Then we have automatic demand management system that's already in picture, where the demand management is made is automatic. That is from the LD based on your load balancing, load generation balance. Command will be automatically issued to the general substations to shed or control the feeders so that the demand is made within the generation, the balance is there automatically. Then we have asset management that is already in operation. We are planning for more centralized, more automated asset management systems. GIS mapping has already been undertaken for HT and HT networks. And we are having around 43 towns all coming under RIPDRP, where all the network is GIS mapped, consumer indexing has been done. And we are going for innovative technologies like HTLS, monopoles, narrow-based towers, then drone-based maintenance management systems, everything in transmission. In the distribution also, we are going for GIS mapping. We are planning for AI automatic meter reading, distribution SCADA. We already have distribution SCADA in 3 towns, in Trivandrum, Cochin, and Calicut, where we are monitoring the network through a remote SCADA system. And distribution transformer and feeder monitoring is already there in 44 towns. All the distribution transformers and feeders in the boundary area of RIPDRP is being monitored through from remote. And we have border meters also for accounting, the energy accounting and audit. We have cybersecurity systems in place. OMS is also in place. Workforce management is there. And distribution PMS, we are, there is a plan for going for distribution PMS also, but it is only in the planning stage. It is not being implemented. Distribution PMS also. Phase measurement units, basically. In transmission, the phase measurement units is being done by Power Grid. It's already in the implementation through 2 phases, phase 1 and phase 2, that we'll talk about later. And under consumer section, we have smart metering. We are going to have smart metering. That pilot is going to come up. Prepaid metering, we had tried for government offices, but we didn't take it up further. Consumer portal is there already. It is there. It's under operation. Payment mechanisms, several types of payment mechanisms are in operation. We are highly advanced in that field. KSCB. Okay, so the challenges, what we are going internationally also, right of way, we are gone up to, like what I told you earlier, 765 kV and 800 kV HVDC, 1200 kV UHV AC is under, it was under construction, but it's not under operation. Aurangabad Varda feeder is there, we constructed 1200 kV. And HT lines we are using, nationally as well as in state also we are using the same thing, 400 multi-body lines, compact towers, narrow base towers, monopoles, and series compensation is being adopted. Statcoms are there in southern region. VSC based SVT system is there in Madagaskar. From Bogolur to Madagascar, we have a 320 kV, 2000 megawatt HVDC station, which is a symmetrical monopole system. And for land acquisition, for reducing the land acquisition requirement, we are going for GIS. We have several GIS gas insulated substations coming into picture now. We are going for hybrid substations also, where you have AES and GIS coming into picture, and digital substation also, where you have compactness in the control system. And renewable integration, we are going for, we are planning for transmissions systems coming in earlier than the generation, so that there will not be any problem for power evacuation as such. The transgrid is mainly meant for that, because all the transmission systems will be in place, so that there will not be any bottleneck for evacuating the renewable power. And we are going for dynamic line rating also. This is a compared new technology in India. We are the first to have a pilot in this sector. We have introduced the dynamic line rating project in Vadatop area, where we have a renewable green wind energy there. So basically, the dynamic line rating is basically dependent upon the ambient conditions, where you measure the ambient conditions and then predict the actual loading that the line can take based on the system conditions like sag, solar radiation, wind speed, again ambient temperature, everything. We look at conductor temperature. We look into this and do a prediction. There's real-time monitoring is there that we already implemented a project, and we have seen that you can have around 20 to 30% more loading in the same line when you have the DLR in picture. And we have strong interconnections also now coming into picture. We have continuous lines, several lines, 4 lines are coming in there for balancing the system. In fact, we have been requested to use our hydro for balance in the renewable in Tamil Nadu. There was a proposal in the southern region for using our hydro systems for balancing the renewables in Tamil Nadu and Karnataka area. So in southern region, there is a plan for establishing the renewable energy management center, control center for renewable forecasting schedule. And this balance and resource like with the hydro is there, power market is there, ancillary services is also there. Then we are going for energy storage also. KSCB also had a plan for energy storage, 10 megawatt energy storage, vanadium based for battery system in Kasaragod, but didn't come up. We had an initial plan for installing those things. Then grid managed, we are going for smart grid, real-time monitoring systems, self-healing systems. VAMS is being wide area monitoring systems using power phase measurement units is being implemented in southern region. Automation substations has already been taking place. AMR is also there. Net metering is already in picture. Demand side management using automatic systems are there in place, and consumer participation in demand side is also being happening. And this same thing we are using for high final temperature conductors, because we are using normally the conductor temperature is only up to 75 degree. The design temperature is 75 degree. We are planning to use for higher rated temperatures conductors. Then multiple conductor bundle for hexa, and basically 765 kV lines are having hexa configuration, but 400 kV we are using cord and twin MOS configurations. Then because it increases stability also. Then we are planning for alternate conductor system like HTLS, INVAR, systems, then we are using dynamic line training system. Okay. So what are the technologies that we are adopting? We are using all the emerging innovative technologies like this narrow-based towers. These are narrow-based towers designed for this thing. It's very compact tower. This is a 400 by 400 K system. It's very compact, and you have insulated cross arms for reducing the right of requirement, so that your windspans will be reduced. That's another technology we are using. Then the tubular towers. This is what I talked about. We already have a system in place from Manjeri. We have 100 K line. Which came up on 60 kV right of way. 60 kV single circuit, 60 kV single circuit right of way. We went in for 100 kV double circuit using monopole towers. This is the tower which is being used there. And we have composite insulators used in distribution systems and in EHV systems. And HTLS conductors. These are HTLS conductors, high capacity conductors being used in almost all the transmission system nowadays, wherever we are facing right of way problems, where we have to go in for the existing same tower and right of way. And we are using covered conductors also. In 60 kV and in 100 kV, we are using covered conductor, which is actually a HM sleeved conductor. We don't require any additional right of way for this thing. This is actually a snapshot from Vietnam, where for the container terminal, for the Vietnam this thing shipping, Vietnam port, we have to ship the lines, and there was no clearance, and we used 60 kV insulated conductor there. And we are using gas insulated substations also. So when we are going for reconducting, the main advantage is that the current carrying capacity for the same diameter and weight, as mechanical properties remains the same. No modification or reinforcement is required for the existing tower. You can have around 1.5 times the existing capacity for the same with the reconducting, with the HTLS conductor. And for new right of ways, we can have enhanced right capacity 2 to 2.5 times higher than the thing, with the reduced per unit transmission cost, higher corrosion resistance, and additional capacity. So this is what happens. This is actually an ACSR. This one side is ACSR and another side is with the HTLS conductor. See here the sag is very high, but on this side with the ACC conductor the sag is very low, but the conductor rating has gone up from 1.2 to 2 times compared to this one. So this is the main attraction of having ACC conductor, HTLS conductor in the circuit. Okay, and you can have increased span also with the same. For new lines, you can have increased span so that the tower requirement will come down, so that the overall cost will also come down. These are the various HTLS conductors available in the market nowadays. When you see GIS, this is actually a 400 by 20 kV substation where the GIS was introduced. What happened was, after the introduction of GIS, you had this much spacing. Only the whole substations will come down like this. So that's the main attraction. Your footprint comes down like anything when you go in for GIS. Of course, it will be at a cost, but still the cost has come down like anything. Nowadays, the GIS cost is not that much. Only 20 to 25% higher is there. 15 to 20% the lower range. And we are going for more. We are planning for modular GIS substations. It is there like this. It is a modular substation. Actually, we planned it for on evacuation system in Naringathod, that is in Iravinjipura basin. Initially, we planned to have this sort of systems or mobile stations there, so that we can reduce the gestation period for substation, because the renewables are coming up, the SHEPs are coming up like anything. They were their construction period was very low, so we had to plan for a cooling substation there. And initially we planned for having this sort of modular GIS there, but later on we changed the evacuation system, and now it is not there. And hybrid substation, this is already in place in KSCB. This is a very compact substation. This is a ABB make PAS substation. It's very compact. If you can see, this is like this. I will just explain how it is being done. So this is basically PAS, and what happens is, this is the CT portion, the outdoor CT, where you have the whole thing, CT, CVT, CT, PT, breaker, isolator, everything in this one unit. So this is where you have the CT, and then you have the PT here in this portion. You have one PT here and another PT here on the incoming portion. This is the bus PT, and you have the circuit breaker in this portion. This is the circuit breaker. Isolator. This is the first bus isolator. Then you have the circuit breaker here. Okay, this is how the whole system has been made very compact. It doesn't require much space actually. So this is the savings part you have when you compare to an AES. When you have 62 meter by 86 meter for a double circuit bay, you require 62 meter by 27 meters for this one. So it has been very compact. The footprint has come down like anything. So this we are using in many 20 kV substations nowadays. Pothangod, Edaman, Nallalam, Padlam. Everywhere we are using the same hybrid base now. And when you compare GIS with the AIS, when you have, if the 100% is required for AIS, Hybrid switchgear requires 50% and GIS requires around 40%. This is a thumb rule basically. So there's around 60% reduction when you go in for GIS switchgear. It's very compact nowadays. And like you said, you implement SAS automation. Earlier days, we used to have a lot of copper cables coming into the picture. Just a mess. Actually, you require more room, more space, more control trenches, cable trenches. Everything should be there. But now, because of this IEEE 618 option, substation automation system implementation, it has come down like anything. We use fiber cables for that, and the requirement, space requirement has also come down. The control room requirements has also come down. It has become very modular. All the control equipment has become very modular. Environment footprint has come down. Design and construction skills has been there, and it has enabled use of IC that instead of non-conventional instrument transformers, we can go in for in conventional, we can go in for optical CTs. Instead of conventional transformers, we can go in for optical CTs, non-conventional instrument transformers. Some of the pilot projects are being done in by Power Grid for this optical transformers, but KSB is set to implement that. And this is another one which is being implemented. Wide area monitoring systems is already being installed in the southern region. It is installed in 400 kV above substation, state and central grid and IPPs, independent power producers, all generating stations from 20 kV level and above, HVDC terminals, and import interregional and international tie lines. Both it will be installed in both ends of 400 kV and above transmission lines of state and ISTS. The phase 1 is being implemented now. Around 1186 PMUs will be installed in 32 with a 32 phaser PDCs, okay, at control centers. Then there will be 460 numbers of PMUs that's already installed at various locations. We will be having in Madagaskar, Kayangolam, and Idiki. And development of analysis is already there. It's already developed and it's under testing now. It is being developed by IIT Mumbai. The analytics for PMUs is being developed by IIT Mumbai, and it's already installed in SLDCs and RLDCs, and it's under testing now. Phase 2, we will have another 550 MUs installed with the OPGW installation. All the communication will be through OPGW. Earlier, we used plan for satellite communications, but because of the time lag delays and all, we are going for OPGW communication now. And KSB is also introducing an OPGW throughout its transmission system up to 33 kV. It's a basically, you all know, it is KFON. It's a KSITL KSB joint venture. We are planning to have OPGW in all 400 kV, 220 kV, and 1 kV transmission systems, including 60 kV. And down the line, we will have ADSs, all dielectric self-supporting cables in 33 kV systems also. So we will have a comprehensive communication network throughout Kerala, which will be a great enabler for going in for smart metering. Because everything, for smart grid implementation as well as smart metering implementations, you require very good communication backbone. And we expect the KFON to provide that. For our protection requirements also, we are going for differential protections for feeders also nowadays due to this availability of PGW. This PDC, phaser data concentrators are available in NLDC and backup LDCs, and super PDCs, phaser data concentrators available 5 RLDCs, because all the PMUs will be communicating to the phaser data concentrators. And from there, we'll go to the RLDCs, and from there to NLDC. So this is the basic architecture that is being used. That's what under implementation. So this is the basic PMU installation. It's basically very compact. Earlier it used to be very big. Nowadays it is available in this simple 90U racks like any other numerical relay. It's very compact now. Even the protection relays are having PMUs nowadays, but it will be with a lesser. It will be only with the 128 samples per second. Normally PMUs will have 256 samples per second data sampling, but the relay-based PMUs will have around 128 samples per second data sampling speed. Anyway, that is more than sufficient for our purpose. So this is what we are having. Then this is dynamic line writing. This is the equipment that is being mounted in the conductor. So this is the line. We're using this particular equipment to mount on this, and we have a transmitter here for having this thing. So what it will do is it will measure the conductor temperature, ampacity, the current loading of the line, sag clearance, weather conditions like ambient temperature, wind speed, wind direction, solar radiation, etc. Emission coefficients, everything will be measured by this particular thing, and communicate remotely, where the algorithm will run, calculating the amount of loading the line can have based on the current ambient conditions and the conductor loading. This is already implemented in Vadutha feeder. The pilot is going on for the last 1 year. This is the first time in India that we are introduced. This is the first pilot in India. KSB is proud to have that. And this is a distributed control and protection container, which is technological updates that we are using. This nowadays the relays and control. Early days relays used to be in the control room, but nowadays the relays are being placed inside the yard, so that you can have lesser copper cables coming into picture. And SF6 insular series are being used. That is also planned for this introduction. The optical CTVT unit, that's still not yet available in KSB, but in the near future that will also be available once the technology matures and the cost comes down. So next we will go into RE thing. We'll be talking about RE integration. Basically nowadays we have around 204 megawatt of solar with the KSB rooftop coming to 6.66 megawatts and the KSB ground mounted coming to 10.75 megawatts. And other projects like government institutions, private, HANEWAT, everything coming to around 196 megawatts, 196.75 megawatts. It's a rough figure basically. This is based on September 2020. So wind is around 70.275 megawatts. Altogether, we have around 274 megawatts of RE power in the system. That's not much. We are there is no basic integration problems with respect to this power except for the transmission evacuation system. Otherwise, there is no operational issues nowadays because of this problem. When it goes beyond 1000, then we can have problem. But as of now, there's not a big problem. But the problem is we are planning to have an additional 1000 megawatt solar by the end of 13th plan, about 500 megawatt through rooftop solar generation. That's a distributed thing where the injection will be through the distribution network, which may have some problems coming in the future. Then we have 500 megawatt through ground mounted floating solar. Again, the main thing with respect to this is basically related to power evacuation, because the floating solar will be coming up in reservoirs, which is basically in the forest area, and we don't have any network as of now. We have to plan for additional network in that area. Addition of wind generation is also expected, around 72 megawatt wind generation is there in the Agadi area. So what we are having, the SPV locations like this, we have Kasaragod 50 megawatt already in service now, 5 megawatt is under execution there. So after 55 megawatt will be there in Ambalappara. Then 50 megawatt is under execution in Paivaliga region. That's going to be commissioned shortly. So we'll have around 105 megawatt solar in the Kasaragod area. There's another 200 megawatt proposed in Chimini. 100 megawatt land is already identified and received from GOK. And another land is identified for 100 megawatts. We have floating solar PV locations in Wayanad, 100 megawatt of Banasur. It was proposed by Seki. And in Idiki, we have 175 megawatt proposed at Anjiruli and Cherdoni, these two locations. Anjiruli is near to Kattapena and Cherdoni is near to Padatopar. There's 50 megawatt is there in Cherdoni area and 125 megawatt in Anjiruli area. That is proposed by NDPC. So there's another 20 megawatt coming up in West Kannada in Kollam. That is proposed by NHPC. So NDPC, NHPC and Seki are planning to have floating solars in Kerala. And wind, we have Palakkad 72 megawatts coming up in by NHPC. They proposed 70 megawatt in NHPC by NHPC in Agli area. The main constraint is evacuation system. We are planning to have a green corridor there up to Manarkot. From Kottatra to Manarkot, to NQ system will be there. So we plan to use that for evacuating the 72 megawatt NHPC project. And basically the connectivity will be to transmission, sub-transmission and distribution system. Here the problem is, transmission is basically from 60 kV and above, and there is power injections for generation as well as import from large consumers. It is a mesh nature, so basically redundancy problem will not be there. Only problem will be with respect to the reactive injections, reactive requirement of the solar, reactive injections related to solar plant and all stuff, because with the solar, we have to back down the conventional generation and hence the reactive support will not be there. And we have to have reactive support from the inverter-based systems to have proper connectivity to the transmission. Regarding transmission, also the same problem will be there with 33 kV and above. We may have faced problems there because sometimes it is open loop and sometimes it is partly mesh. There also we can have bidirectional flows. And in distribution system, we have 400 to 33 kV. Basically, here what the problem is mainly with respect to unbalanced loading and low voltage, which is basically radial, very lengthy lines. So having distribution in the RE generators in the faggot can have voltage problems. The main challenges are related to two domains: integration of utility scale RE resources to transmission grid, both EHT and sub-transmission, and the integration of distributed RE resources like rooftops SPVs in the LTM, because we don't have any wind coming up in distribution systems, or mainly it will be rooftop SPVs coming up, and that will distributed things. So prediction of power from this, the energy from this will be a big problem. See, when there's any deviation in the active power, it will have frequency deviation. That's the main challenge that we're facing, because there's high variability in the renewable power. So frequency deviation can be very high. and the reactive power requirement, because basically these generators, solar generators, they don't inject reactive power as such. All utility scale generators, they're going for only active power injection. They hesitate to have reactive power injection, even though the capability is there. The people who installed the 1 megawatt, 1 MVA solar inverters, they won't provide reactive support as such. So that will create voltage deviation issues. And there's no there's heavy uncertainty in the race, because there is no clear-cut forecasting available now for this RAs. So there will be fluctuations in active power supply, frequency leading to frequency diversion, and there will be degraded capacity of frequency regulation, because when we have higher penetration of renewables, you'll be backing down the conventional generators. So we will not have sufficient capacity for regulating the frequency. The generators at bar will not be there, so that we will have problems in regulating the frequency, just because most of the renewables are not dispatchable as such. And reactive power is needed to stabilize voltage, which won't be available. And the EVs, that is another big headache which is going to come. Electric vehicles, we have to plan for them, because they reshape the demand pattern, because they can come up at any point of time, at any point of the grid. So it will have temporal and special patterns also. So they have to coexist with the congestion and because that will create underutilization of grid components also. Of course, we have to plan for meeting these loads, but these loads will not be there most of the time. So there will be excessive implementation of the grid component, grid elements for meeting these demands, and that will remain underutilized most of the time. Likewise, also with respect to solar, if you don't have battery storage, what happens is you have to design the transmission system for catering to the solar, which is available during that time. And since the loading in Kerala is comparatively low, we have to have system for exporting the system, these things. But what happens is so most of the time what happens is the major transmission system as such will not be utilized, because we will have distributed generation everywhere. So the demand will be met locally. So the transmission system will lie idle. But we have to plan it for the peak load also. So we have to excessively plan it for peak load, where the utilization is only for 6 hours. So there will be underutilization of the grid components. The ICTs, the transmission systems, higher voltage lines will remain unutilized most of the time. That is happening in southern region as well as all over India. Most of the 765 kV lines are lying underutilized. Only 8% to 10% loading is there in most of the 765 kV lines. They can carry around 4,000 megawatts plus loading per circuit, but only 800 megawatt is being found there nowadays. Basically, there are several 4,000 megawatt solar installations coming into picture, and most of the demand is met by those power plants. This will bring the associated power loss, frequency, and voltage deviations also. So this I'll skip this slide because we don't have much time. I think I have already gone over my time. Here we see renewables are fundamentally unpredictable. This everybody knows, and there is no tools available for long-term forecasting this thing. That's a big operational issue. So we cannot have economic dispatch also because of this. And it is not the value actually. How much installation you have, how much installed capacity you have, but it is the intermittency that is creating the problem. You can have any amount of renewables that if you can dispatch it properly, but intermittency will create problem for grid stability. And the wind cannot be curtailed. That is another issue which will really later on provide produce transmission congestion also. This is another problem, ramping down. If the wind generation comes down, so you have to ramp like anything. Huge ramping capacity will be required. If the renewable comes down, and again when the renewable goes up and the load comes down, then you have to ramp down. So fast ramping and fast ramping up will be called, ramping down and ramping will be called for. When you have a large penetration of wind, or rather solar renewables, you may require large capacity for ramping down and ramping up. So that will be a bit difficult. Basically, hydro will be the most essential thing, but many places hydro is not there. Okay. And most of the renewables have short gestation periods. Wind maybe having 6 to 10 months. Renewables, solar maybe having 4 to 6 months, something like that. And with the max only they'll come up. But transmission grid element addition will take time. And variable intermittency there's already then reduced system inertia is another big problem we are facing. These renewables, these solar inverters, they don't have any inertia. They will not put any inertia into the system. The fault load will be converted down. When you bring down the conventional generations, the fault load in the buses will come down. So the voltage regulation is directly dependent on the fault load. Higher the fault load, better the voltage regulation. So when you have a reduced fault level in the system, because of the backing down of conventional generators, your voltage regulation will be very poor. So it will move like, the voltage will move to the extremes like anything. So for that, we have to introduce virtual inertia. That means you have to go in for energy storage systems to produce inertia into systems. Actually, not actually, virtual. Actually, we are. You have to introduce this thing, battery energy storage systems to produce the required inertia to the system. And the low utilization, that is already I had discussed, the low utilization factor for the transmission systems. So this first picture, this is basically the solar variation, and second one is the wind variations. So this, if in the southern region, there's around 1600 megawatt wind variation during one particular time. So for one day, so from say around 2000 megawatt has come down to around 500 megawatt or something like that. So there's a huge variation in wind generation on the same day. So that's a big headache. So we require what we require for proper forecast. We require real-time data on grid congestion, dynamic line rating, energy production forecast should be there, and all the ambient temperature. We would require a very good weather forecasting system so that you can have a real good renewable forecast also. So it's directly dependent. Unless and until you have good weather forecast system, you won't have it real-time accurate forecasting for the renewables. And the line conditions are also very important. So there are some snapshots of the variations, just for your information, is how the daily wind generation pattern changes in Tamil Nadu. You can see that there is huge variation in wind. And again in Karnataka, same way in Karnataka also it is almost the same. So everywhere it is the same. So it can be typical for Kerala also. I don't have data for Kerala, but it's almost the same. Likewise, solar also, this should be the ideal pattern for solar. But what happens when you have cloud and rain? Actually, that will go like, that will vary like anything. And cloud is more severe than the cloud and rain. In cloud and rain, at least you can have a constant variation. With the cloud only, the variation will be very intermittent, unpredictable, totally. So this is actually one thing from our Ambalitra solar output. This is for a particular day on 19th, recent only, 19th of November. See the variation in solar. This is on particular day. Again, this is for another 3 days, 13, 14, and 15. See the variation. On 13, there is huge variation. And on 14, there is a small variation. 15, again, there is another variation. See, like this is highly intermittent. It's unpredictable totally. So when you have huge solar potential, how do you manage this thing with the conventional generator? It's very difficult to adjust to these variations. So you have to have a limit on the renewable penetration as such, so that the system operation will be more easy. Again, when you go in for distributed solar, rooftop solar also, you can see the same thing. This is a 150 kilowatt plant. It's a 30 kilowatt plant in Aircode substation. See the variation for a particular day. This is what is happening. So when you have a cumulative distributed generation, this sort of variation will be, when you look at a higher level, this can have a big problem when you have this sort of distributed generation constant on a particular area. This is for Madagatra. Again, 750 kilowatt peak plant. See the variation again here. It has gone from 110 kilowatts to 61 kilowatt. This is a small variation only, but still. Again, this is another day on 7/11. See the variation. And again, this is the same thing, 9/11. And the third day, that is for 7/11. This is for 9/11. Again, see the variation. See another day, 4/4/2019. So this sort of variation will be always there. This is what we have to account for when you plan for the renewable energy dispatch. So we will have reduced for this already talked, reduced fault level, reactive power issues will be there. Then the fluctuations, because of the low fault level, there will be voltage regulation will be very poor. So there will be very big voltage fluctuation. And I will show a study case which happened in KSCB grid that I will show you shortly. There will be voltage imbalances because of single phase injection because when you do single phase injections in distribution grids, there will be voltage imbalances. Then the voltage rise will be there at the fag end. There can be voltage rises, and reverse power flow will be always there. So the protection systems has to be redefined or redesigned to carry out to cater to this thing, particular phenomena. Because all the protection systems were designed for in the distribution system. It is designed for radial power flow, one-way power flow. Now we have to plan for reverse power flow also. Then power output fluctuation will be there. Frequency variation regulation will be there. Power quality, harmonics, and DC injection issues will also be there. Because with a good quality inverter, this may not be there. But if you have the flyby operators playing in the field, where you have installers coming in the picture, installing this thing with the low cost inverters and then disappearing, then you can have a lot of harmonic and DC injection issues coming in the picture. In safety concerns, anti-aliasing features are also there. Because now we really have concern on this, because in our normal load on the distribution system, in the LT system, in the urban, at least in the urban areas, the loading of the LT lines will be very, very low during day period. only fridge will be there, because most of the houses will be, people will not be there. They'll be going to office, and loading will be or they'll be going to school. So the loading will be very, very low. And at the time, if you have multiple solars coming in the same grid, and if the islanding is not proper, then you can have anti-islanding concerns. It is recorded in Hawaii. Several places it has been recorded, but let us see. We hope for the best. Nowadays, the anti-islanding has that algorithm has developed to a very good extent. So there are a lot of active anti-islanding schemes available. So this problem may not occur. We hope for the best. And this is the normal water. This is one case which I am going to explain to you. Actually, this is the normal water level as per the grid code. For 400 kV, it should be between 420 and 380 kV. What happened was, on last March 2019, Karnataka faced around 80 to 90% grid penetration. So they had huge wind and solar available at that point of time. So they backed down all the conventional generators during the daytime, basically. They backed down all the conventional generators, and only the wind and solar was there, which was around 80 to 90% penetration compared to the normal demand. So at the time, because of this, there was high voltage in many of the areas. So what they planned for putting the irrigation loads in the picture at the time. During that particular time, they called all the irrigation, because they have a system where they can bring the irrigation loads into picture. So they called all the irrigation loads in the system. And because of the irrigation loads, because of the motor starting, and because of the lack of inertia, lack of conventional generation in the system, the fault level was very low, and the voltage regulation became very poor. So there was huge fluctuation in the voltages. When all the irrigation pumps came into the picture, there was huge fluctuation in the voltage. And what happened was, day voltage profile became very, very worse. And system voltage went down to 357 kV. See, 380 kV was the minimum, and it went down to 357 kV. And the system was on the brink of collapse because of that problem in Karnataka. See, that Karnataka renewable injection has created a problem in Kerala. That's what happened. So we had a near miss event at that point of time. Then we suddenly brought all the hydro into picture. We brought up the IEEE generations into picture, and somehow we stabilized the whole thing. So that is a very critical event related to renewable. This was highlighted in many discussion forums also, this particular event. So this was the voltage profile. See, it is coming down like anything. This is one particular voltage profile in Madagascar. And this is another voltage profile in see, this is another voltage. It has come down to 370. This is 380 kV, very poor voltage profiles. So this is basically related to the renewable injections in Karnataka, where when you brought down all the conventional generators out of bar. So how do you address this integration challenges? We will be planning for green energy corridors for evacuation of the powers, and for controlling for having a better interconnection of the balancing areas. And we'll go for wide area measurements, so that we have better situational awareness. The angular measurements will be there, so you can have a better angular situational awareness, and you will have better visualization of the grid parameters, and you can have a stable optional grid. Then we are planning for renewable energy management centers. It is actually, I'm talking about southern region in general, not only in Kerala, because Kerala we don't have much penetration. There we will have a renewable energy management center, which will go in for renewable forecasting, SCADA for RE generation, and scheduling of RE. And nowadays there are plans for battery energy storage systems also. We have a 100 megawatt battery energy storage system in Australia now. We have another 10 megawatt in, I think it is in Delhi by Tata Power. So it is being tested nowadays. Maybe case we also come up with the battery technology, because we had an initial discussion with the NDPC for this floating solar to have battery also along with the floating solar. I don't know what is the current status as of now, but initially we had a discussion on that. Then we have the smart technology implemented. Transmission is already having the smart technology. We have real-time free dispatching is there. Dynamic line radius is already there. Pipe projects are there. Interflow control is there. HVDC link is there in picture. Special protection schemes is already there for backing down the generations, depending upon the RE injections, or bringing up the generations at a faster rate, ramping rate. And the wide area monitoring system is also being implemented. Then we can go in for smart technology in demand side measures also. That we are already implemented through ADMS. We have the smart grid. Hopefully this may come into picture. When you plan for integrating the DG, you have to look into the existing structure of the network. Like what I told you earlier, is very important. Size and location of existing generation, size and location of the loads, whether the generation will match the loads, whether you have upstream injections or there will be there or not. Then you have to plan for that. Then you have to plan for the DTS distribution transformers based on that. Then the impedance of the various sections, so that depending on impedance you can see whether the voltage regulation will be there, whether the voltage profile will be good or bad, that you can see. The time availability and the variability of the DG has to be ensured. That's one of the important thing. Then type and location of the existing protection systems. You have to relook at the protection systems before integrating the DG. Then the effect of DG at the proposed location, then whether it will increase the fault level or reduce the fault level, whether it will have voltage variations coming into the picture, whether there will be voltage rise or voltage dip. Those things we have to study. These are some of small systems, interactive systems only. That's what is being used currently everywhere for almost all the rooftops without any battery storage. This interactive, grid interactive system is very easy to interact with the PV system with the utility. That we are going in for large scale implementation. Then you have this coming up shortly. It will be coming up the energy storage systems, PV with energy storage. This is going to be a headache basically, because then you have to plan for protection systems based on this. Several difficulties will come into picture when you have the battery storage also, because in the other case what happens is here, when once the grid is not there, the solar PV will be disconnected, will go out of the system. But here what happens is, even though the utility is out, the PV system will be maintained. The grid, the inverter will be maintained. They will maintain supply. So you have to go have higher protection systems coming into play. It will create some problems in the network. See, this already I discussed. The IEEE, this chemical safety hazard, as I told you earlier. If it backfeeds and energize the power lines, already with the diesel generators in place, we have several accidents happening. So this, I don't know whether it will enhance it or that we have to see in the near future. And when you have single phase output, like I told you earlier, when you have single phase inverters installed in the consumer premises and it injects, already the system is unbalanced. When you inject the power in the system will become more unbalanced, or it may become balanced also depending upon the network condition. But the more chances you have unbalance in the system, which will create unbalanced loading voltages also. That you can see in many places, because in some places the voltage is going beyond the normal limit during daytime because of the renewable injection into single phase. When you have a three-phase system, you can see, if you watch your energy meter, you can see this phenomena. In some phases, the voltage will be very high. In some phases, in my house, I have voltage up to 260, 280 volt in one phase and 180 volt in another phase at the same time. So this such variations I have already observed. Then there are several codes for integrated internal connection requirements. IEEE 921-1547 is the series is there. Then again you have UL underlaid laboratory 1741 is there. Then NEC Article 5690 is there. There are several standards for this interconnection purpose, which defines what should be the minimum requirements for interconnection. There are regulatory requirements in India also. Grid codes is there. Then connectivity regulations are there. Technical standards for grid connectivity is there. Then standards for connectivity of distribution generation for 33 kV and below is also there, where they insist for several conditions before connecting to the grid. DC injection should be less than 0.5% of full rated output at the point of common coupling. Then harmonic limits should be as per IEEE 519. Flicker not to be beyond that specified IEEE 6100. So these are the regulatory requirements. Again, some regulatory requirements are also there. Now the system shall be capable of providing dynamic reactive power between 0.59 95 lag and 0.95 lead. This is not maintained by many of the inverter systems that is currently in place. And they should be capable of operating in the frequency range 47.5 to 52 hertz, because they should not get disconnected when the frequency fluctuations are there. Because what happens is, since your conventional generators are not there, and if this generators also, if this REs also get tripped out, then there will be huge imbalance in the load generation balance and consequent collapse of the grid. So they should be capable of operating this region 47.5 to 52 hertz, and they should be delivered. They should be able to deliver the rated output at 49.5 to 50.5 hertz. So these are regulatory requirements. And wind generators, there is a special condition for generators at 6 kV and above. They should remain connected to the grid when the voltage interconnection point on any or all the phases dips up to the levels deprecated by thick lines. That is between 0.15 to 0.8, 15% to 85%. So this is the time 300 milliseconds to 3000 milliseconds. If it varies, then it should remain connected to the grid. So the condition. There are several international regulations also. IEC 61727 for Europe, IEEE 1547 USA, and VDE 0126 for Germany, where they specify. Actually, they are very stringent. When the utility voltage is outside certain limits, plus or minus 15%, the inverter should cease to energize within 0.8 seconds to 2 seconds, depending on the standards. More severe under overload lead to shorter intervention times. That's this basically for anti-aliening protection. So again, the frequency domain there is a constraint, and they have specified harmonics, reactive power, DC in the current injection, earth current, anti-aliening, etc. also. So there's a clear cut compared to India. The international regulations are very clear in this aspect. Even the distribution inverters, the distributed generation inverters in Canada, in some places, need to be smart inverters. In many places, they're insisting for smart inverters nowadays. In case we have planned for that, I don't know whether it will be implemented smart inverters, because they'll be capable of providing real-time reactive support and voltage support to the grid as required through dynamically. So this is what we tried actually. This we have already tried in Ambalatara. When we had a real shortage of reactive power issue during the crisis in summer, we insisted that because there it's a ABB make reactive inverter system there, 1000 kVA, 1 MVA reactor inverter is there, which has got reactive power capability also, day and night reactive power capability also, because almost all the current inverters are basically voltage source inverters, current controlled voltage source inverters. So that you can easily provide, because they have a DC system in the background for controls, for stabilizing the DC bus. Capacitors will be there. So they can use this capacitor system for providing the required reactive support to the grid. And since we insisted, actually this is the first time in southern region also, because earlier nobody was giving that, but since we insisted, the Ambalatara, because it was a joint venture between KCB and this thing, so we could insist on that, and we got around 16 MVR support from this particular unit during the time. So it was a great help for us. So what happened was, it proved that this is capable of providing the reactive power support without any issue in the active output, without degrading the active output. Their main concern was that when they provide reactive support, it will degrade the active output. But the inverters were rated for 1.1 MVA, so that they could give the reactive support without degrading the active support. So now even the southern region, they are going for discussion with other inverter, other solar power persons to provide this reactive support from the inverter system. This is basically a singular diagram for that particular inverter in solar ABB inverter, is PSC 800 series inverters. So they have both day and nighttime capacity. Even during nighttime, they can provide reactive support, because they will be drawing power from the grid to charge the DC systems, these capacitors, and then they will be providing the reactive support to the grid. It's very easy for them. Since it's a BSC-based system. So with this, I come to the end of my session. You can have a questions in this session now.
I think it was, we are all overwhelmed by the fantastic presentation from Engineer S.S. Biju. Actually, it's actually, as Chandramohan sir was pointing out, it's a feast actually to the power engineers and renewable energy engineers, as well as the academicians, research scholars and all. It's like a knowledge coming from a hub. It was flowing from all the sides, so we are thankful. And I think we are already late, but still, because a lot of people are there still, so I think the session for question answer session is open now. I think the team can coordinate on the question answers now.
Shweta.
Thank you so much, sir, for the session. Now the question answer session is open. The audience who are having the questions, please post it down in your chat box. Your questions are really valuable. Sir, one of the participants actually requested for the...
I lost your sound. The speech is not clear.
Oh, I'm sorry, sir. Sir, one of the participants was asking for the presentation slides. Is it possible?
Yeah, sure. I'll send it to you. Brought me email ID. I'll send it to that. Okay.
Yeah, you can Biju sir,
I'll send it to you.
The chapter. Okay. You can send to the chapter so that we can publish it.
Okay.
As Bobby
sure,
sir, the secretary was telling out. Yeah.
I'll do that. I'll do that.
Thank you so much, sir. Sir, there was an interesting question in the chat box. If they are having a new type of electricity generation method, what are the possibilities of starting a startup in the renewable energy sector?
Actually, KSB had an innovation wing where a lot of such proposals came up. When there was a lot of wonderful proposals, a lot of you can say lot of unconventional proposals also, like generation from electromagnetic field, generation from the earth, gravitational forces, through Venturi effects. I mean, lot of proposals are there, and in case you consider many of the proposals. But now that particular thing is not there in KSCB, because we had a startup zone in Cochin also, where we encouraged to have these things. But for the last few years, it is not actively in place. But this sort of thing can be come up, because if you have a proposal, you can bring it to the KSCB's notice, and we can bring it to our planning wing, and they will certainly support it. That's not a big issue.
All right. Thank you so much, sir. Sir, the next question. What is the estimated transmission efficiency of Pugalur-Madagattara line?
Actually, the Pugalur-Madagattara line is a HVDC system. So basically, the losses are almost negligible there. It is part AC line and part cable system. And the losses will be around normal related loss will be around 2%, 1.2 to 2%. That is what is expected in HVDC systems. It will be highly efficient line. Basically, there is no skin effect. Nothing is there. It's only purely DC. So actually, it will be the same as like any other HVDC system. Around 1.2 to 2% will be there.
Sir, the next question: is there any project for pumped storage scheme for the state, as we have surplus power and we are having many hydro units?
Actually, we planned for that. We had planned for one in Idiki, because one second stage is coming up in Idiki. Actually, a new project is coming up in Idiki. Another 760 megawatt project, 780 megawatt project. The second new stage is coming up in Idiki, and we planned to have it as a pumped storage, actually with the Francis turbine. But somehow the cost didn't work out. When you went into the economics, it didn't work out. So we shelved that project. Another project we planned was at Damalayar. That also, because of this, there are this resettlement of tribal, because a tribal colony cannot be resettled twice. That's some issues there. So that also didn't materialize. As of now, there is no plan for pumped storage in KSCB system. Because basically, if we get support from the ministry, there's a funding system there. From the you have a energy fund. If you can get funding from that, then we'll plan for that. Otherwise, no, we don't have anything for as of now.
All right, sir. The next question: is there any proposal for installing suitable SVCs in northern Kerala to meet the VAR deficiency?
That's an interesting question. Actually, this I forgot to tell you. We had a diesel generating plant in Kozhikode. Kozhikode diesel power plant was there at Malayalam. But the machines, almost all of them, except for two machines, almost all of them are now not working, redundant. And we are planning to have synchronous condenser there. That we are actively pursuing. We will be putting up around 100 megawatt synchronous condenser, 100 MVR synchronous condenser at KDPP. Statcoms, SVCs we are not planning, because SVCs are highly dependent upon voltage. Their output is highly dependent upon the voltage. So since the voltage profile is very low in the northern region, SVCs will not be of much use. And as I told you earlier, the inertia is also not there in northern region. So what we will be planning is this synchronous condenser and hopefully Statcom for Kasaragod area. We will be going for Statcoms instead of SVCs, okay, because Statcoms doesn't depend upon the voltage for their operation.
Okay. So the next question: in the next 5 to 10 years, demand will increase with EV penetration. How do we manage the grid stability with solar penetration up?
Actually, that is a problem which we have to explore, because we don't have the spatial data. How much the EVs will be coming up, how in which locations it will be there, because the charging locations, everything has to be planned basically on that. But we are hopeful that the existing network will be more than sufficient to make it. But we need to have a demand side management system also, so that these EVs will not come into picture during the peak time. We have to suitably have the tariff based on that, so that the demand will be shifted to the off-peak hours or during the daytime when you have more solar coming into picture. That some sort of arrangement has to be planned, but as of now, since the EV penetration is not that much, we have not looked into that. Okay.
Okay, so the next question: is there any plan for offshore wind farms?
As of now, no, we don't have. Earlier we had a plan for micro turbines in Vizhinjam area, but that also is dropped because it was not feasible. And on the long run, we came to know that it is not feasible, so we dropped that also.
Okay, sir. Is there any methods to predetermine the stability issues in grid connection for a distributed generation system using any algorithms and simulation methods?
That is where the distribution PMS, DPMS will be helpful, because we may have to plan in the long term. Most utilities will have to plan for that DPMS, distribution PMS, so that you can have the angular stability of the distribution grid also visible. You can have more visibility in the PMS, because that will help a lot to integrate the distribution generation in the distribution grid. So that's one way you can have the dynamic stability known earlier. They are going for DPMS.
All right, sir. So the next question, it was mentioned that EV penetration can lead to spatial and temporal patterns, and hence we should expect localized peak at any time of the day. As we expect large penetration of EVs in the recent future, how is KCB preparing for that to avoid overloading, unbalance, and voltage management?
Basically, see, transcript project is meant for this, because we'll be having a lot of substations and lines coming into picture. So that as such, transmission system will not be having any problem in meeting this huge demand, because we are planning it for around 8,000 to 10,000 megawatt for meeting the future. Up to 2030, we will not really face any problems as such. But distribution side, yes, we can have problem, because we have to have plans based on the EV concentration, where this, that's what I'm saying, this special configuration has to be known in advance, because that planning is not at there, not even under policies also. So those things has to be taken into account while planning for the distribution system, and we will suitable plan once the policy decisions are in place. Once we will know clearly as to what will be the amount of EV penetration that is going to happen, because it changes from policy to policy, it will change. But once it has to stabilize it, then only we will go in for that. Nowadays, that like solar, the EV penetration is not that much that is concerned. It is very much concerned to us. Once it comes up, like it will take time basically. So on that time, we will plan for the distribution system also. But transmission system, as there is no concern as of now.
All right, sir. So what are the possibilities and opportunities of microgrids in Kerala?
It's good. Actually, KSEB's main plan was to have 100% electrification, so that there is no need for microgrids as such. But again, there are several places, several colonies, Adivasi colonies, where you can have microgrids. Even remote hamlets are there, where supply stability is not there, only radial feeding is there. There's a lot of scope for microgrids basically. Definitely, it should be looked into.
Okay, sir. So what is the reason for solar PV price to become negative?
That is a question I don't know how to answer, because I don't know whether because it has come down like anything. But nowadays, because of this, central government policies, like because now they have some more something like on the this PV equipments. I am not sure about that. I'm not really. You can ask these things to the renewable people which are going to come up now, because I am not clear about those things. Okay, so.
Okay, sir. So one more question. What are the problems associated with grid connection of distribution generation system?
That I clearly explained. There are few things. Like one thing is in distributed systems, already your systems are unbalanced. The loading is highly unbalanced. And many places you don't have three-phase connections. Most of the households are having single-phase connections. And they will be going for single-phase injection of renewable power. That can create a lot of unbalance in the system, both loading wise as well as voltage wise. And our HT-LT ratio is very poor. We have long, lengthy LT lines. And when you have the solar injections at the fag end of the lines, there will be a swells and sags in that particular line. Voltage profile will be highly uneven. That can also create problem for you, because at the fag end, the voltage, the fault level will be very low. So the voltage regulation will not be there. Again, the voltage fluctuation will be very high. And in other systems where you have when you have a large quantity of renewables coming into picture, then you have problems with the injections, upstream injections, reverse power force. Then you have to look into the feeders protection systems to rework. You have to re-engineer those things. You have to re-engineer the DT distribution transformer ratings. Again, when you have large scale of inverters, there will be harmonics injections in the system. Then you have to look for the transformer failures, and you may have to go in for K-factor rated transformers, to avoid these things. But there are several issues that can come up when you have large quantity of renewables coming into picture. As of now, it is not a big problem. Maybe around 1,000 megawatts injection, then we can have a problem.
All right, sir. So that is all of the questions. I think we are good to move on. Thank you, sir.
Thank you.
Now I invite Dr. Bobby Phillips, sir, Secretary IEEE PS Kerala Chapter, to take over the mic for the vote of thanks.
Distinguished dignitaries, PS leaders, and dear participants. So it has been, as Ajit Gopi sir mentioned and Chandravan sir mentioned, it has been really a feast to the power engineers and power and energy enthusiasts. So he has actually dealt with this topic, that is renewable energy. In addition to that, he gave a picture of the transition that is taking place in Kerala's State Electricity Board. So in terms of the technology addition and the new kinds of devices that is coming up, he gave a light, and yet it was he dealt with the complex issues, but the presentation was quite simple. Any person could actually, without prior knowledge, could easily get some of the concepts. So, on behalf of IEEE PS Kerala chapter and all the attendees of this seminar, I thank you, sir, for coming over here. And in fact, he was given the date in a short time, so he cooperated with us to respond to our request, and he came forward to present this within a short notice. I thank sir, for a wonderful presentation.
Thank you.
I would like to thank the PS leaders who are really the architects of this webinar series. In fact, we have been planning it for quite a long time to have an increased engagement with power engineers of KSCB Limited, because that will surely benefit both the power engineering community, professional community, as well as the KSCB Limited, for sure. And I thank all the leaders, Davudan sir, Chandravan sir, and Suir sir, for clearly planning this program and helping us carry out it in a very effective manner. Next, I would like to thank Ajit Gopi sir, again, who has been the real coordinator of this program. He has been actively designing the program, making the contents, and has been actively engaging with the experts to get time and arrange everything in a very nice and effective manner, so that the delivery of the topic was very effective. I thank him on behalf of the chapter and the attendees. Next, I would like to thank the participants, volunteers, and who attended the program for making it a very grand success. And we will surely meet again tomorrow at the same time, and you can use the same link. Those who are interested can use the same link to join at 7 p.m. tomorrow for the program. Thank you all.
Thank you, sir. It was indeed a great opportunity for all of us to hear from you, Biju sir. Thank you.
Sir, okay.
Sir, please carry on.
Bobby sir, you are telling something.
No. I just wanted to hand over the mic to you so that if any message is there, you can proceed.
Anyway, it's a great opportunity for all of us, and special thanks to Biju sir, VKD sir, and all the veterans, all the leaders, Chandramohan sir, Bijana madam, and all the great leaders, IEEE leaders, and faculty assembled here. And Bobby sir and all the team, student team, all the IEEE PS, young professionals, for making it a great success. And actually, I request all of you to attend the further sessions. No? Tomorrow we will meet again at 7 p.m. for the wonderful session from Engineer B. Pradeep sir. Actually, he will be speaking on the changing role of utilities. So again, I would like to thank Biju SSR for coming with a very short notice. And we are grateful to Biju sir and KCB Limited for this wonderful session. Wonderful session. Thank you. Thank you again.
Thank you. Thanks so much.
Yeah.
Thank you all who have joined, and join us back tomorrow for the second episode. Thank you and have a great evening.